This is hydrothermal coordination model. So it's next in the canvas. And that deals with taking into account in the medium term the uncertainty regarding hydro availability, hydro natural inflows or natural hydro inflows. Okay. So first, medium term, what that medium term means, which is the time scope regarding medium term. What medium term means? Months up to a year, okay? Why? Because again, a year is a natural time scope, okay? Things, the humanity, we move on a yearly basis, okay? And therefore, we are scheduling the operation of the system for a year. For example, now we are in January, we can try to determine which is the schedule up to the end of this year or 1 year in advance, okay? So we are running the model today in order to determine the optimal operation for the next 12 months or for the next 11 months until the end of the year, okay? That is the idea. Why this is sensible? Because we have to manage hydro, okay? We are receiving water in our reservoirs, and we need to decide when to produce that electricity. When will be worth it to produce it? First, when you are receiving water in your reservoirs. Okay, when it's raining? Spring, typically spring. So in the northern hemisphere, we'll be in spring. Most of the countries rains a lot in spring, in the northern hemisphere, okay? So, and we receive a lot of water. What happens if we don't have a storage capability? We must produce as we receive it, okay? What happens if we have infinite capability for storing the water? When is worth it to produce it? Okay, so you are connecting with the cell. So when the prices are higher, you are trying to produce. We are providing you with cost minimization models. However, the point of view of the company will try to maximize its benefit, its profit, okay? Therefore, they will keep the water at the reservoirs in order to produce when the prices are higher. When do you expect the prices are higher? For example, in winter, for example, every day, let's say in the morning and in the afternoon, you have solar production. So you are trying to keep the water in order to produce and to substitute, that essentially is related with the prices, the electricity prices, the most expensive thermal generation, okay? So you are keeping, and this is the type of decision you must take with this type of model. So if I'm having enough storage capability, I will keep the water in order to substitute the most expensive generating unit in the next 11 or 12 months, okay? What happens? Again, huge uncertainty in hydro availability. We don't know in advance how much water we are going to receive in the next 12 months in our reservoirs. So if we decide to produce a lot now, maybe we cannot use that water for substituting in September, in November, expensive generation. If we decide to keep the water now and we receive a lot of water in 3 or 4 weeks or in 2 months, then we can spill the water because there is not enough storage. Okay, so these are the type of decisions we must manage with this hydrothermal coordination model. I'm going to skip. This is a video where they are saying basically that you must use the water in order to substitute the most expensive generation. Okay, so why hydro generation is very relevant? Flexibility. So as you have discussed previously, they are able to start up the generating units almost instantaneously, to ramp up very quickly, and to shut down very quickly. So they are able to modify its production and adapt it to any kind of profile, demand consumption profile. Okay, so that is very, and on the other hand, the operational cost is negligible. Basically, they have no operation cost. There are minor operation costs, but there is negligible with respect to, for example, fuel cost of the thermal units. So, which is the drawback? The drawback is the uncertainty. We don't know for the next 12 months how much water will be available for us in the reservoirs, and therefore we will not be able to make sure that our decision is the best, given that we have uncertainty in natural inflows. Well, all of you know that we are storing the water in dams, and we are taking the advantage of the potential energy in order to convert them into kinetic energy and to produce electricity. Okay, that is the basic mechanism. Some difficulties: variety of the sizes. Okay, Javier has mentioned that Endesa, a particular company in Spain, has 240 hydro units in Spain. Okay, that means a huge number. Here we are saying that we have 800 units with more, 800 units in Spain, and 80 of them are bigger than 50 megawatts. And we have a large variety of them, from 1.5 megawatts to 900 megawatts. Okay, so we have very small hydro generating units and very large hydro generating units, and we need to manage. If we consider the CCGT power plant, we may have two flavors. One is 400 megawatts and the other one is 800 megawatts, or even bigger, but there is not a huge range of variation in the capacity of the thermal generating units. A nuclear unit, 1,000 megawatts, even 1,200 megawatts, but this variety is not as large. And also, for example, regarding the storage capability, we have a storage as small as 0.15 cubic hectometers and 2,400 cubic hectometers. So again, the variation of the storage capability of the reservoirs of the hydropower plants is large. And regarding for example, the water we are able to store, this is the biggest reservoir in Spain for hydroelectricity production. This is full capacity and this is empty. In 2017 or 2024. So huge variation. We can have a huge variation in the operation of the reservoirs or in the water safe at the reservoirs, depending on the year. If we see the location of the different hydro units in Spain, they are all over Spain. And in this particular section of the course, we are going to deal with two things. One is additional with respect to what the model we have previously seen. One is the topology, so the complexity introduced when dealing with the hydropower plants that is related with topology, that has also been mentioned by Javier. And the other thing is with the stochasticity. The energy we receive in the reservoirs as hydro inflows, okay, can be very uncertain. And therefore, we need to deal with that in our model, okay? So that's why we call this model a stochastic hydrothermal coordination model. First, the topology. So these are real maps, or maps of real rivers in Spain. and you can see one main river and other tributary rivers. The blue corresponds to the reservoirs, more or less proportional to the size of the reservoir, okay? And these ones are the power plants. When you have a double arrow, means that you have the pumping capability. You can generate or you can pump the water from another reservoir, okay? And this, so you see that there are bigger reservoirs, or there are other smaller ones, okay? So depending on the size of the reservoir, you have more flexibility to produce energy or not, depending on that size. This is one river. This is another river, again with several tributaries, with some pumped hydro units, with some generating units. This is another river, okay? So these are called cascaded hydro reservoirs because some of them are above, upward, or downwards than water other reservoir. Therefore, if you are releasing and you are producing electricity with one reservoir and is reaching the downstream reservoir, you must take that into consideration in order to produce or not to produce with the downstream reservoir. So this is, for example, a set of two reservoirs in the northern part of Portugal with some pumping capability expressed by this double arrow. This is the largest hydroelectric complex. We have a conventional hydropower plant with a conventional reservoir, and this is the upstream reservoir or upper reservoir for pumping. So we are taking, or they are taking, water from this reservoir and save in the above reservoir. So by doing this, you have the flexibility of pumping or turbining, therefore consuming electricity or producing electricity. So all these things, topology must be taken into account. Instead of dealing with, let's say, what we have, what Javier has said, that is, in the previous model, we were ignoring the network, the electricity network. They were considered single node or copper plate models, okay? Now we are extending, taking into account the topology of those reservoirs, okay? This is the uncertainty regarding hydro inflows, okay? We have 4 columns, the year, here it says hydro energy. What do you think that is hydro energy? Anybody tells me? Yeah, what means hydro energy in this table? For every year. It's in terawatts hour. Is the second column. The amount of water that we have received, okay? In theory, let's say, if we receive a certain amount, typically we spend that year, in that year we spend that amount of electricity, of hydro energy. However, if our reservoirs are very empty, we can keep, or we can refill those reservoirs. So in theory, we must spend what we receive in a year, but however, some of this energy can be moved backward or forward, okay? And what is the range of variation? So we have a smallest value in red as 13 terawatts hour, 14 terawatts hour, and higher values in green as 41. So in 1 year, we receive from water 41 terawatts of energy, and in another year, we receive 13 or 14 terawatts. So this is the huge variation between the energy we have received, the reservoirs have received from the water, okay? So huge uncertainty. Remember that for wind, we mentioned that the uncertainty in the yearly basis was plus minus 2%. Here, we are saying that is plus minus 50%, 50%. Okay, the mean value will be something around 26, 27, we will see that number. And what is there, this column? This column means is index. So is the variation with respect to the mean value. Okay? So for example, this 41 is 141 times the average historical value. This is 55% the average historical value. Okay? So the range of variation in the amount of water we expect to receive in 1 year can be half of the mean value or 1.5 times the mean value, or 1.4 times the value, that value, okay? The uncertainty is huge. That happens in Spain, that happens in the US, that happens, again, in all the countries that have, let's say, basically two seasons, spring and fall, where we receive the water, okay? And this is the cumulative probability function, okay? So that means that this value, there may be some inconsistencies because they are updating the mean value, the mean historical value, okay? But that means that 16 terawatts hour is going to be exceeded in 95% of the time of the future years, and 37 is only going to be exceeded 70%, okay? So it's the probability of having that value or beyond, okay? So this slide says there is a huge uncertainty in hydro availability, hydro inflows from 1 year to the following one, okay? So we cannot say, last year was wet, therefore this year is going to be whatever, average, dry, or wet, okay? No, there is no correlation from 1 year to another. What happens in the northern hemisphere? In the northern hemisphere, the hydrology years start October the 1st, okay? So the connection between the previous year and the following year stops in September, at the end of September. So what has happened previously has nothing to do, or may have nothing to do, with the following starting in October, okay? Let's see in more detail these values, okay? Again, we are plotting here the production. Instead of terawatts hour, they are in gigawatts hour, but the values are the same. The smallest one is 13 terawatts hour, and the highest one is 41 terawatts hour. And you can see that there is no specific pattern in the evolution of dry, wet, average, etc. years along the time, okay? And the mean historical value is 27 terawatts hour, and if we convert that energy into constant power, will be 3,000 megawatts. So the energy in Spain, the average hydro energy in Spain, is equivalent to 3 nuclear units producing the 8,700 hours a year, okay? This is again histogram and the cumulative distribution function. There is not too many data, and the profile doesn't seem to be very nice. This is the same as we plotted for the wind. So the 12 months, when it's raining, when we receive the water, in spring, in fall, and nothing in summer. But however, you can see that there is a huge uncertainty in the water you are going to receive in a certain month, okay? And here is the mean value. So the dark curve, so here is the mean value. What that means that essentially we are receiving low amount of water, however, from time to time we receive a lot. So this is not seen clearly here, but it should be like this. So it's like a log normal distribution. So most of the years are dry, but from time to time we receive a lot of water. That histogram is not perfect. This is the box plot corresponding to, again, to the same values. And this, you see the evolution, these are the reserves, okay? So the amount of energy stored in the reservoirs for every month in a year for the last years. Okay, we have the historical mean value, this dark blue. We have the lowest value, the lowest historical value for every year, and the highest historical value for every year. Okay, so this will be the lowest value for, let's say, October for the last 30 years. That will be the highest historical value in May for the last 30 years. Okay, so the envelopes. Okay, and the light blue are the real evolution of the reserves along the time. Okay, so for example, here we started 2019 below the mean, however, we ended above the mean value. What that means? That year we receive more than the average natural inflows. Here, we started a bit above the mean value, but we ended far below the mean value. That means that we receive far less than the average value, average natural hydro inflows. And here, we started, let's say, a bit above, and we also ended a bit above. So more or less was an average value, an average historical year. Okay, so you can see the relevance of optimizing the hydro production along the time. You can see that also we have touched minimum values, for example here, and we have also touched maximum values. So in 2022, at the end of, we were having the lowest possible values in the reservoirs, and 2 years later, we ended with all of them at full capacity. This corresponds to the reservoir level in percentage along the time. So let's say historically, we start January, let's say around 50%, 50-something percent. Some of them were very low, some of them were very high, and we try to end also at 50%. However, the evolution of the reservoirs makes this profile. Basically, we are receiving the water, we try to keep that water when it's better valued, so for the highest period, highest prices period. However, we need at the end to produce on that follow. When dealing with uncertainty, we must deal simultaneously with the hydro inflows in different regions, in different reservoirs. Okay, so for example, I'm presenting here 4 reservoirs, the hydro inflows of 4 reservoirs in Colombia. Please observe, on one hand, the profiles. So this profile is totally different than this profile, and is different than the other profile. Okay, so that means that some reservoirs are receiving, let's say, Atlantic, let's say, rainflows, and some others, or Caribbean rainflows, and some others are receiving Pacific, from the Pacific. So they may have different behavior along the 12 months. But at the same time, see the y-axis scale, okay? 300, 1,000, 1,000, 30, 40. So in an scenario tree, that will be the way to represent that, we need to consider the different profiles, okay? And at the same time, the different scales. That the reservoirs are much more relevant because they are receiving a lot of water. However, this reservoir, let's say, is irrelevant because it receives small hydro inflows. So we need to consider correlation. Given that we may have different regimes for receiving the water, some of them will be more correlated than the others, okay? And therefore there can be some correlation among these hydro inflows due to the geographical location of those reservoirs, okay? We need to consider the amount of water they are receiving. So some of them receive a lot of water, and some of them may receive a small amount of water, okay? So, and we need to introduce all this information in what we call a scenario tree. This is just a question of how much that the climate change has happened, okay? So we are receiving, in Spain, we are receiving less water in general. The red ones will be a decrease in the water received in certain areas, and there are almost no blue areas. So, stochastic optimization. Again, what will be deterministic optimization in this context? The deterministic optimization, we will say, we are going to receive exactly that amount of water on every reservoir for the next 12 months. So, exact values, typically the mode, typically the mean value, typically the median. So, single values for the 12 months for every reservoir. That will be the deterministic problem, where we are considering single values for all the parameters, in particular for the hydrant flows. What will be the stochastic approach? We don't know what are going to receive for the next 12 months. However, what we receive will have exactly the same statistical properties that we have observed in the past. Okay? So we don't know in advance what we are going to receive. We are going to receive, for example, some scenarios, a variety of scenarios that will evolve along the time, but that the statistical properties of the assumptions we are making about the probabilities and the values of that scenarios will correspond or will be similar to the historical data. Okay? That means that, in particular, we are not considering too much climate change effect. So this is the difference between this type of problems are called here and now. Okay, we must take the decisions right now, not knowing in advance how much water we are going to receive for the next 12 months in the reservoirs. That will be some kind for a single reservoir, that will be the scenario tree we want to get, okay? This will be, instead of a single branch in a single set of values for a single reservoir, we are going to have. We need to take the decision right now. We may observe for the next month or for the next week, we may observe two possible values of hydrant flows, 20 cubic meter by second or 25 cubic meter by second. This one with 45% of probability and the other one with 55% of probability. In the following week or month, we will have another two branches, two openings. Then we may receive 35% of 35 cubic meter by second or 25 with these two probabilities or these smart values. First, we are plotting this for a single reservoir. We will have as many of these trees as reservoirs, each one with different values, okay? Some of them we will receive more water than the others. And then we are also seeing the time dependency, the time correlation, okay? We are in a branch where we are receiving less water in the first month and also in the second month. Those values are lower than the above ones, okay? So we need to consider a spatial correlation because the reservoirs may have some correlation because they are closed, for example, and temporal correlations. If this week is raining, then the following week will be also raining, okay? Basically, this is the... Okay, let's explain how we determine the scenario tree. We present the scenario tree generation as a clustering procedure, okay? Everybody knows what is a cluster? I guess so, okay? You are not in groups, but if I need to find some cluster centroids of U, and I need to, for example, select 3 clusters. One will be located here, representing probably these people. Another one can be located here, representing these people, and another one somewhere in the middle, representing the other people. Okay, so that will be a geometrical clustering process. Okay, so the same idea is for hydrogen flows. We need to cluster in the time domain and in the geographical domain, spatial domain. Okay, I'm going to present just the clustering in the spatial domain, but can be extended to the time domain. So here we have inflow in reservoir 1 and inflow in reservoir 2. Okay, the blue dots correspond to the historical data, so for a certain period, so in January. How much water they have received, those 2 reservoirs they have received in the last 30 years. Okay, we see that there is some kind of negative correlation. Okay, so the slope is negative. So when this reservoir is receiving a lot of water, the other is receiving less water, and vice versa. Okay, so there is some negative correlation. We have decided to represent this cloud of blue points by means of 2 centroids, 2 clusters. Okay, these 2 clusters are the triangles, the red triangles. Okay, how we do the clustering process? Let's assume that we are moving those triangles, okay, in order to define or to find this position where the distance between the blue points and the corresponding triangle for all the blue points is the minimum one. So we are minimizing the intracluster distance. Okay, so that means that for these 5 people, we are selecting some position over here that minimizes the geographical distance among this centroid, this representative, this cluster, and the 5 people assigned to this cluster. The same for these 4 people, and the same for the last 5 people. Okay, so these triangles minimize the sum of the distance. The location of these triangles minimize the intracluster distance. So for all the clusters, we are taking the distance from the blue point to the triangle and minimize for them. Okay? Once we have decided the optimal position of these triangles, this is the typical k-means algorithm. Okay? So we take, on one hand, the probability. So the number of blue dots associated to that triangle will be the probability of this cluster. The number of blue dots associated to the other triangle will be the probability of that triangle. Okay? So here we have the probability of this cluster is that we have 2 possible values for the rain, for the hydrogen flows in this reservoir 1, either 50 or 25. The historical data were represented by this probability density function. However, we are discretizing those values, this cloud of point, in just 2 possible values, 25 or 50. So that means that either rains hydrogen flows as 50 cubic meter by second or 25 cubic meter by second. Okay? There are no more possible values. We are discretizing all the historical data. And in the other reservoir, either, let's say, it rains, has hydrogen flows as 45 cubic meter by second or 25. The probability of this value is the number of cloud points associated to that triangle, and the probability of this value, the length of this row, is the number of blue dots associated to the other triangle. Okay? So we have discretized, like obtained these 2 things. We have obtained the value, the 2 possible values, and the corresponding probability. So generating the scenario tree will be to determine the best tree for all the reservoirs, for all the time scope, that best satisfies the historical data. So we are like moving, changing the values of probabilities and changing the values of hydrogen flows in order to have exactly the same properties, mean, variance, etc., the same statistical properties as the historical data. Okay, so that will be the scenario tree that we use to represent the stochasticity in our model. Yes?
What is the, I understand the point of discretized density function, but what is the point of finding centroid?
The point is finding those values and these probabilities. So,
for that you don't need a center.
yes, the center determines the probability of this arrow that corresponds to this number of points divided by the total number of points. This arrow will be exactly the same length probability of this arrow. The probability of this arrow will be the probability of the other, okay? And the center, yeah.
And may I add, sometimes when building these scenario trees, you can compute the centroid, so like the average of all the observations that fall into the same cluster. Another technique could be to select among the existing samples that belong to that scenario, which is the one that is more close to the average. So like, you know, in that example is very simple because it's only one dot.
Okay.
But if you are creating a scenario, for instance, for inflows for a whole year, the average in every month is not really a realistic scenario. So it's better to consider a realistic scenario that took place in the history, in historical records, okay, that holds some properties that makes this scenario to be realistic in terms of having the possibility of being in reality.
These are the natural inflows for a certain reservoir, and you can see that we start in October and we end in September. Okay, why? Because the fall and the spring are in the middle. Okay, these are, let's say, 16 or 20 historical observations, and this is the scenario tree. This is the scenario tree. This is the structure, and these are the real data. So we have a single branch here, we have 2 branches here, we have 4 branches here, we have 8 branches here, and we have, let's say, 16 branches here. Okay, and I can go back and forth, and see how are they comparable or not. What happens if we reduce, instead of 15 scenarios, we reduce? This is the same, but with lower number of scenarios. 1 branch, 2 branches, 4 branches, 8 branches, and no more. Okay, so if we reduce the size of the scenario tree, we are representing, instead of using 3 clusters for all of you, I use only 2. Okay, we are increasing the inaccuracy, we are increasing the intra-cluster distance. So, for example, here, that was a project we did in collaboration with MIT time ago that corresponds to the hydrogen flows in Iceland, okay, Iceland. Where the hydrogen flows come in Iceland? Well, glaciers, so snow melting, okay? Okay, what happens? June, mainly in June. So again, that means that this is June, okay? So this will be again October or September, and then in June. This is winter, and this is spring, okay? Above we have the historical data, and below we have the scenario trees. So the scenario trees are similar to the historical data. We try to represent when the uncertainty happens with a reduced number of branches representing that uncertainty. Okay? This type of model will be, instead of dealing with 1 week, 1 day, will deal with the full year. And in particular, we have make a lot of simplification. This is not done nowadays. However, for, let's say, the prototype purposes, we are dealing with load levels. So instead of dealing with the chronological curve, we are dealing with the low duration curve, that will be the purple one, and we discretize, we convert that into piecewise function. That means that we are, instead of dealing with, these are 5 days, 24 hours, that will be 5 times 22, times 24. Instead of this, we are dealing with 3 load levels in order to make simpler representation, okay? Therefore, will be 3 load levels for weekdays, 3 load levels for weekends, for 12 months. That means in total 72 load levels, that will be far less than 8,000 hours 700, okay? So we are dealing with 12 months and 6 load levels per month. Very simplified model is peak, shoulder, and off-peak, peak, shoulder, and off-peak. First for the working days and then for the weekends, okay? Therefore, we are simplifying the 672 hours of a month with just 6 load levels. That makes much easier for a prototype to deal with the size of the problem, because we are focusing on the scenario trees. I'm going to stop here and we will continue tomorrow. We will start tomorrow with half an hour of the same topic, okay? In order to make able to continue with the formulation, try to understand, and also installing a prototype. In this particular case, the prototype is written in GAMS. I don't know how many of you are familiar with GAMS or interested in GAMS. It's another type of algebraic modeling language. The installation of GAMS is very easy. Just download and double click, and you have the license in Canvas. Okay, we have.
Sorry to interrupt. In the slides of the unit commitment, although I didn't explain because we didn't have time because of the translation, there is a detailed instructions on how to install GAMS and how to activate the license. Okay, in my slides of this morning.
So you have a temporal license for 3 months provided by GAMS, and the installation is very easy. Double click, and then it will install somewhere in your computer. So it's much easier than installing Python or any library in Python, okay? Thank you very much. Sorry for the snow. It has caused a lot of problems for us and for you, probably. And thank you for attending the first day. That is very brave for you to come here with the cold weather that we are having.
And a final message before we leave, sorry. Yes, I mean, we are very open to attend your needs. So if you have any specific need, through Pablo, you send a message to him, and we can try to organize the rest of the week to accommodate to your needs in your research or whatever. This is the purpose. Tomorrow we will start with, we will continue with the network, and Roy McDonald from MIT Energy Initiative will explain that generation expansion planning. So, well, you have the detailed program, but we are very flexible, so we can accommodate our contents to your needs.
Typically, we can attend any of you to have some talk with us in the E19, that is the MIT.
Okay. Thank you. Thank you. See you tomorrow.